it will be too detailed and maybe boring to go through all the work that we did in the PhD and the work, day-to-day work that is done at Intel. So I wanted to give a more generalized version of the semiconductor industry and how it all started and where are we now and what we should see in the coming years or decades and so on. So as Amit said, I did my master's and bachelor's from Kanpur, but I never thought about going for a PhD. But as interest evolved, mine evolved, and I went for a PhD, got a PhD. Then from there, I was fortunate enough to get a what's this request? Someone is requesting to annotate the content. Okay. Sure. So yeah, after PhD, I mean, I was fortunate to have good advisor in PhD who gave me good freedom to work around, and we had lots of fun and fun discussions, fun work. And from there on, I joined Intel in capacity as a yield engineer. We worked on the latest node over there, and with that, again, my interest started evolving, and I transitioned to a system validation engineer where we do the content validation for all the latest products that go into the market. But nonetheless, let's begin this small presentation on the state of affairs with semiconductors in the last century and coming years. So semiconductors, as we know, I mean, the most commonly known semiconductor is silicon, but the semiconductors are not restricted to just silicon. So I'm here giving a brief glimpse into what can be considered a semiconductor here. So there are elements in the periodic table from group 2 to group 6. Mostly single element semiconductors that we see around are group 4 semiconductors, silicon, germanium, and even carbon is a semiconductor if you have the correct crystal structure. So as you see, like graphene got a lot of noise some time back, got even a Nobel Prize on it. And if you think of it, your diamond, even the jewelry diamond, can be used as a semiconductor if you dope it correctly. So the only thing differentiating between a semiconductor and an insulator is that semiconductors you can transmit a large amount of currents at a certain voltage point. So there's a turn-on voltage for semiconductors. So below which it will act as an insulator, above which it will be a good conductor of electricity. Then we have these compound semiconductors. You can make compound semiconductors just based on the group 4 elements. You can make silicon carbide, which has a large application in the power electronics world. A lot of power diodes are based on silicon carbide. Since its band gap is higher, it can uh, take on a large amount of voltage across the junctions. You can have silicon germanium, which has been used successfully in the transistors that we use in the microprocessors and all. Other compound semiconductors comes with combining group 3 and group 5 elements. You get semiconductors like aluminum arsenide, phosphides. You get aluminum gallium arsenides, phosphides, indium phosphide. All these have been studied well, and most of you read LEDs and so on are based on these semiconductors, and even the red lasers, the laser pointer that you use in your presentations and all are based on phosphide arsenide semiconductors. At the same time, you can also combine these metal elements with the nitrogen. You get nitrides, which again is an interesting semiconductors which I studied a lot during my PhD work. So I'll throw some light on it later on. At the other end, we have group 2 and group 6 elements. You can make them into selenides, tellurides, sulfides, and so on. They can also be used as semiconductors. And now, I mean, sometime back, a few years back, there was great interest in looking at oxides based on group 3 and elements. So aluminum oxide, uh, gallium oxide, and all those various combinations, they're high band gap materials. So yeah, there is a lot of combination that can go on. You can create different nanostructures based on these semiconductors to tune their properties. And so basically, semiconductors would differ in the crystal structure, band gap, which is a very important metric of the semiconductors. Smaller the band gap, you'll get higher mobility of electrons and all, but at the same time, your breakdown voltage will also be lower. Your electron and hole mobilities are important in terms of how much current you can transmit and what can be the speed that which you can transmit it. And of course, the dielectric constant, which becomes really important when you are making laser structures, because you need to get the correct reflection of the light across so that you can get the inversion and you can get a population inversion in the channel to get the lasing effect. But all these semiconductors, they have really enabled our day-to-day life today as we know it. I think 40 years back, no one thought we would have smartphones in our hands, which would be as powerful as a NASA computer and the Apollo spacecrafts, and so definitely, I mean, these materials have had a large impact on the current life that we are having. Looking at the semiconductor market, it's always looking to be growing all the time. So from traditional segments like just personal computers or the office computers, the microprocessors are going to be used in a large variety of areas. Like you already know, there is a lot of effort going into automotive sector where you get the automation in the driving, like self-driving cars and so on. At the same time, you got all these electric vehicles which need a powerful chip installed on the car to take care of all the processing that goes behind. So this is just a simple example. Then you have all the things in your home, right? Your Bluetooth speakers, your Alexa, Google Home, and all those voice activated commands that take voice activated commands, those modules. Everything has to be connected, and they all need a chip inside them to connect to one another. So definitely the market seems to be growing as ever. I mean, it's supposed to breach $500 billion just next year in total for the microprocessors. But this is not just the single market for semiconductors, right? I mean, microprocessors just form one segment of it. There's a whole other field in optoelectronics where LEDs, laser diodes, optical sensors, you get silicon photonics going on. So all those also seem to be growing a lot, like visible LEDs that you see in your at the back of your phone in the form of a flash. That's based on a semiconductor, right? Gallium nitride. That's actually a blue LED. It's just coated with a phosphor and that shines light, which looks like a white light. Similarly, laser diodes have a lot of applications. Like conventionally, lasers have been developed in the using gases, right? Argon laser, xenon laser, or xenon neon laser, those kind. So this is a miniaturization of those lasers into laser diodes, which you can carry in your pocket and use it for different applications, right? A lot of this can be used for even data communication. So there are efforts to create miniature laser diodes onto a certain semiconductor wafer where you can transmit information by light instead of electrons. And as we know, light has the highest velocity. So it can increase the data transmission rate a lot. Going to the history of the transistors, I think it's really fun to know. Like transistors, when they started, it was not the goal to create a computer out of a transistor. The three scientists that are given credit for this invention of the transistor, Shockley, Bardeen, and Brattain, were actually working at the Bell Labs. They were trying to create a switch that can replace the conventional mechanical switches in the telephone exchange. So AT&T Bell is a still a big telephone company over here, and for its continent communication from the east coast to the west coast, it would have different stations in between, and switching used to create a lot of loss, and also it used to occupy a lot of space. So that's what their target was, to create a fast, efficient switch from a semiconductor that they have been exploring for quite a while. So the first image that you see over here is the first transistor that they created. So it was just a piece of germanium which was connected from source, drain, and so on. So based on this, the other companies started licensing the technology, and then the transistor industry just exploded. You got transistor radios, you got the first IC by Texas Instruments, and you got different companies. Fairchild, byproduct of Fairchild became Intel. Like the founders of Intel were all employees of Fairchild before that. And Intel also initially it was mainly focused on RAM production. About more than 30 years back, it changed gear. It went into microprocessor development and production, and that's where we see a really bump in the technology, right? I mean, you start going with the Moore's law. So Gordon Moore was a founder, or is a founder of Intel. So he just stated a law that every 18 months or so, the transistor density should double. So it's not a physical law, it's not a law of physics, it's just a statement, but people have been going to the beat and just following that. It also creates a goal for you. Okay, you have to work towards lowering the the increasing the transistor density. So everyone has been trying to keep it going. And in the process of doing that, there were very many changes that came into the design of the transistors. So initially, transistors were all planar. You could, I'm only talking about the MOS, by the way, I'm not talking about BJTs and also. All the MOS transistors were planar. You would have a source, you had a drain, and on top, in the region between source and drain, you would deposit a gate and control the channel over there. But with time, it became necessary that to have more control over the channel, you need to create another geometry out of it so that you can have lower leakage as you shrunk the size of the gate. There came the introduction of the FinFET. So Intel pioneered the FinFET into the conventional microprocessor chips. But before that, it had already been. I mean, industry had already been funding FinFET research and development in the university since early 2000s or late 1990s. So it wasn't a surprise when it came into mainstream, and Intel launched the first product in 2011, desktop processor out of that. So the difference is that instead of having a planar geometry, you have a fin, and the gate goes around the gate metal goes around the gate channel over there, so that it can control the electrons more effectively over there and cause less leakage and better switching. So based on that, I mean, we see a lot of companies as well, like working on these transistors. So Intel transitioned to FinFET from 32 nanometer node onwards. Like from 22 nanometer node, it was a FinFET for Intel. So other companies like TSMC, which is a major player, Samsung, Global Foundries, they also created their own nodes out of FinFETs. Here we are seeing a trend that shows that, okay, I mean, we are trying to keep up with the Moore's law. Every 2 years or so, we are doubling the number of transistors on the same area of the chip, which is kind of increasing the transistor density by double. And on the right, I'm just showing an image of what the FinFETs actually look like when you take a cross section of the material. So this is actually the fin, the two fins over here. This is the gate metal on top of the fins. And then the channel would be coming out of the screen. The source and drain would be inside the screen and out of the screen. So one way to reduce the or increase the transistor density was to decrease the width of the fins. So that's what they did from 22 to 14 nanometer. And then the next generation is 10 nanometer that is, I think, already out in the market. But the other way is that even if you reduce the transistor fin width, you need to still account for the interconnects, right? I mean, if the interconnects are as large as the previous node, it won't create a big benefit for that transistor density. So the other effort goes into decreasing the size of the interconnect lines as well, because all these transistors, you create logic, right? You create from a single transistor, you create a CMOS. From CMOS, you create gates, NAND gates, NOR gates, OR gates, and then you make it into certain kind of logic that can do computation for you. And all of that like goes and connects to the input and output pins on the chip somehow. we can look at it in terms of like, okay, you say you live in a country, then you have a state, then you have a city, then you have a colony, and then you have a house, right? So that kind of connection needs to be made whenever signal is being sent or received. So with these two efforts going on, I mean, we have been able to continue with the Moore's law. But yeah, this is about transistors. The other end of the semiconductors is about the optoelectronics, right? So optoelectronics, the LEDs,
Excuse me,
lasers, they work
sir.
on the basic principle where you are injecting carriers across a band gap, which is found in semiconductors. So holes are injected along the valence band and the electrons on the conduction band, and then they combine across the band gap in the depletion region. And the emission wavelength is going to be the band gap of the semiconductor. For the lasers, you create a population inversion, so you can get a gain and you get a single peak of lasing over there. So LEDs, lasers, and then obviously solar cells, optical sensors, and all. I mean, these follow the same fundamental principle where you have to either convert carriers into light or light into carriers. So it all began like more than a century back. A British scientist, Henry Round, was the first one who observed that when he put current on a silicon carbide block, he could see yellow emission. But it took a while for this phenomena to get analyzed and then get a working LED. So almost 50 years later, we got our gallium arsenide based infrared and red LEDs pioneered by Nick Colonnack, and so on. The arsenides and phosphide, they exploded in terms of which spectrum they can get. You get all the spectrums, yellow, green, orange, red LEDs from these materials. But one critical part of the visible light spectrum, the blue region, was still missing because the arsenides and phosphides don't have a band gap high enough to get to blue region. So the relation between band gap and the wavelength of emission is that the higher the band gap, lower the emission wavelength that you can get. So for that, we needed a gallium nitride LED, which could allow blue emission, which is around 400 nanometers or so. So in 1970s, work started with the first demonstration of a GaN LED, which I heard is still working even now. If you put current across it, it's stored in some university lab. And the problem with that LED was it was really, really inefficient. A large amount of voltage and current was needed to get emission out of it. The problem was you were not getting enough holes into the structure. So Suji Nakamura, he was a Japanese scientist. He worked day and night for more than a decade on this problem and finally found the solution and demonstrated an efficient PN junction for gallium nitride, which turned into a blue LED, and for which he was awarded the Nobel Prize some few years back in 2015 or 16, I remember. And this work led to the field of nitride LEDs. So GaN PN junction LEDs became indium gallium nitride, laser diodes, LEDs, and only time it was a matter of when we would venture into the ultraviolet regime with these materials, because nitrides are high band gap materials in the gallium nitride and algan compounds. So you can get practically from 210 nanometer to 400 nanometers of emission from these materials. But as is, I mean, all these products, they need manufacturing, right? I mean, we can all think about concept in the lab and then maybe execute it to show like, okay, we are able to get the phenomena working, what the theory suggested, we could get it, but we have to also fabricate it into working products. So I would just touch upon a few simple basics of what the semiconductor manufacturing is all about. Like, there are two fundamental principles that go into any semiconductor manufacturing. First, you have to create a pattern. Second, you have to either deposit or etch on it. So, how to create a pattern? So, this is a simple way to explaining how we can create a pattern. You can think about it as you how you used to develop a film in a photography lab or studio when the digital cameras were not around everywhere, when we used to use a film camera. So here in a semiconductor industry, you take a wafer, you apply resist on it. It's a photoresist, is a kind of a organic material that is sensitive to light. Then you have masks with you, right, which can hide a certain point of area and expose the other areas on the wafer, which is coated with a photoresist. So what you do, you take the mask and you take light, most likely ultraviolet light, and you shine that light through the mask onto the wafer that is coated with the resist, right? You expose certain areas of the wafer, and those areas, depending on how the nature of the material is that we have coated on the wafer, they, when we go and develop them, they can either be edged out, or the areas that were not exposed, they can be removed. So it goes both way, all right? And once we have that pattern on the resist, now we have to transfer that pattern from the photoresist to the actual semiconductor wafer that is lying underneath. So that's where the etching or the deposition comes, right? So the first three steps is and the four steps is still the same as in the previous slide. But in the fifth step, what we can use for etching material is you can use a wet etchant, right? Like oxides and all, they are etched very easily in hydrochloric acid or hydrochloric acid on all those different solutions. But you can also use dry etching in the form of a plasma. So what you do, you take it into a vacuum chamber, you excite the gas inside, most likely a noble gas like argon, or if you want to introduce some chemistry into it, you can introduce chlorine or oxygen into the chamber, and then you ignite, apply a large electric field across the gas, and the gas will become ionized. It will create ions that will then bombard the structure and etch away the material. Another thing is, like, instead of etching, you can deposit material, right? You need metal to be deposited to make contacts. So the principle is the same. You can either do a electroplating and then dip it into a solution to remove the resist that is left over, so it will remove any metal that is not intended, or you can do a evaporation of the metal onto the surface in a vacuum chamber, and after that remove the resist, and what you're left is with the final pattern printed onto the semiconductor wafer, either in the form of an etched surface or in the form of a deposited materials like metals or even oxides and so on. So this process is what gets repeated time and again to create all these microprocessor chips or LEDs or solar cells or lasers and so on. Like in Intel's that interconnect picture that I showed, right? There are like 10 or 11 layers of metal on top. So it's a lot of processing that goes into creating a single die that goes into like all your computers or smartphones, watches, and everything. So as I was talking about manufacturing here, like I also had the fortune of looking at manufacturing really closely by working in a lab environment. My PhD work was on actually doing a crystal growth for three nitrides and then fabricating them into LED structures and finally testing them for their wavelength and efficiency and then their applications. So I would like to show this small picture that we have from my graduate days. Like this is a really old picture now, 5, 6 years old. But what you see is a machine and some people fooling around with it. But that's not the case. It's we are actually sitting on $1 million equipment over there. So this equipment was used to create layer by layer deposition of the three nitrides, or the gallium nitride or aluminum nitride or indium nitride material, and grow crystals out of it. Generally, I mean, silicon and all, you grow crystals in the form of a bowl, like you just lift out, like you deposit sugar crystals or so. But for research and even for other compound semiconductors, you tend to go into the direction where you have these crystal growth machines. So we used to take care of the machines ourselves, would do regular maintenance on it. And it used to be like, okay, yeah, if the machine breaks down, your research stops. So you have to be really proactive in taking care of the system. So the three nitrides that I was talking about, they are really special materials. Uh, One reason is that no other family of compound semiconductors has such a large range of band gaps. So right from aluminum nitride, 6.2 electron volts band gap, to gallium nitride, 3.4 electron volts, to indium nitride, which is a zero point 0.7 electron volts, we get band gaps that go from deep ultraviolet to infrared region. Another important property of these are word-side crystal structures, and due to the special property in them for polarization, you can create high electron mobility transistors out of it, which is the leading application for these nitride semiconductors at the moment. But at the same time, the pace is picking up on the optoelectronics, because these nitrides are direct bandgap semiconductors, which have high efficiency for carrier combination to give out light. So we explored these nitrides for ultraviolet LEDs, since it's still a problem to get efficient ultraviolet LEDs. So in that process, we were looking at novel structures and what can we do to give some more efficiency to these LEDs. And so in that process, we looked upon quantum structures in the form of quantum dots. So quantum mechanics, I think we have studied in the literature that, okay, the most basic form is you have a well, you have a barrier, and in the well you will have quantized states. You will see depending on the thickness of the well, you will have the different number of quantized states, and at the same time you can see that the energy level will go up or down as you change the barrier thickness or the well thickness and all. So what we tried to do over here was grow gallium nitride quantum dots. So that would be the well or the dot that would say, and then in between of aluminum nitride crystals. So aluminum nitride is a large band gap material. So these band gap diagram that you see over here, this is aluminum nitride over here. This is gallium nitride in between. And depending on the thickness of the quantum dot over here, we could tune what would be the wavelength of emission coming out from this LED structure. So the left graph that I'm showing over here, it's a photoluminescence spectra of the structure. So what you do is normally, what is the color that you see with your eye, right? Whatever the surface on which the sun reflects on, right? You see the trees to be green because out of all the wavelengths that the sun is focusing on the tree, you see only green to be reflected back. So photoluminescence is the same fundamental principle. You shine a laser that is a lower wavelength, and you check the wavelength of the reflection from the sample. So what we would see when we shown a laser on this, as we decrease the size of the quantum dots, the wavelength of emission from these structures was decreasing. It went all the way from 274 nanometers to 234 nanometers. So that is what we expect from here, right? If you decrease the size of this well, this energy level should go up. And that was clear indication that we were getting quantum mechanical effect into these structures that we were growing. So the next step was to test it out by injecting current into the structure. So we fabricated LEDs. So this picture you see is actually a LED structure that we fabricated. This small pin-like is a probe that is coming onto the LED and injecting current on it. The other probe is at the bottom of the structure. So this glow is coming from the LED because in spite of all our good work, it would still emit some blue wavelength. And your normal camera cannot capture ultraviolet, it can capture blue. So it could capture that emission from this structure. And this graph over here shows us as we increase the current that was being injected into the structure, the light intensity went up, and this structure was tuned to emit at 243 nanometers. So we could clearly see that the 243 nanometer peak starts going up and up as the current injection was increasing. Another thing we used to confirm that we were actually growing the correct thickness of the gallium nitride was transmission electron microscope. So transmission electron microscope works like a film projector. It's like you put a film in the front and you shine light through it, right? And then on the projector screen, you see whatever was on the negative being projected onto the white screen. So similarly, in the transmission electron microscope, what you do is you create a very thin sample that you want to look at, and you shine electrons through it. And you have a screen below that captures these electrons. And since electron wavelength is really small, you can see like structures in atomic details. So each of these dots over here would represent atom of the structure on the that was under observation. It's an representation. It's not actually an atom. So it's like what we are seeing, and that's where we could do some contrast imaging and find out like, okay, gallium nitride is growing like in the form of a half a nanometer or 1 nanometer, and similarly aluminum nitride was 4 nanometers. So that was the barrier thickness, and this would be the quantum dots thickness over here. So this kind of led to two papers and many more other articles in the literature. And my advisors, they are currently at Cornell, and they have a group working on this whole phenomena even now. So there's a lot of work still to be done on these UV LEDs. At the same time, we tested these UV LEDs for real world application. So like recent news, we all heard that we can use UV light to disinfect surfaces and all, to get kill COVID-19 virus in fact. And that is true. Like if you have a UVC light, which is light that is below the wavelength of 280 nanometers, you can basically kill bacteria and all the microbes that the light is shown on. Um, Kind of, it can also damage you if you get exposed to it. So that's why it has to be done really carefully. So we did a small experiment with a very well-known bacteria, Escherichia coli. It's a bacteria that causes a lot of gastrointestinal diseases in the world, and it's mostly spread by contaminated drinking water. So one of the main applications that is being looked at for ultraviolet LEDs or ultraviolet light is to disinfect water in remote areas and so on, where clean drinking water is not available. So we created a homemade apparatus to carry out this experiment. So we put these bacteria into a small vial and brought our LED structure on top of it and injected or focused the UV light onto that vial containing the E. coli bacteria. And the way to find out if it is getting desired effect or not, we took help from the biology department in Notre Dame. And one way to do it is that you create a petri dish that has the food for the bacteria. So what the bacteria will do, if you put it on the petri dish, it will eat that food and it will multiply. So the strategy that they use was we used a control sample, and what they do is like going from right to left. Each of these dots is the bacteria colony being created. So you take that vial that has the E. coli, you put a small drop over here, you dilute it by 10 times, put another drop, dilute it by 10 times, and another drop, and again dilute. So by the time you are over here, you are diluted 10 power 5 times. So as you decrease the concentration, you definitely see that the size of the bacteria colony decreases. So around this number 5 over here, you see that there is no colony of bacteria existing, barely there. So that is the control sample. Now, the same sample, when you had UV light shown on it, you can see that at number 4 itself, the bacteria was not there. So it seemed like it decreased the E. coli population by 10 times when we had the UV light focused onto the E. coli sample. So that clearly demonstrated that, yes, we had achieved the desired effect. And it also shows that the lab work that we do, it's not about just research that we do in an isolated environment. It has real world applications, and a lot of the work that we see in the industry right now started off in the labs somewhere, either in government research labs, both in US, India, or in university labs, or in the R&D departments of each of the companies that are being used to that needs that can be done. There is a lot of scope in semiconductors, and with every new technology, new applications come out, right? When we developed this LEDs, no one thought that you would get LED displays and all. But if a new technology is invented, people think of new applications. So that's why there's still a lot of work to be done on this, and in decades to come, we'll see what all improvements and new applications come with it. So yeah, with that, I would like to conclude the presentations and go for any questions that are there.
Hello, hello,
Yeah, hi.
hello. Yeah, Dr. Jay.
Yeah, hi.
Yeah, are you listening?
Yeah, yeah, I'm.
Yes, sir. Can you explain that? Is it possible to make LED with perovskite? A lot of people are working on that, but what are the point of stability and what kind of effect it will give?
Um,
And
I
in
think
case of
there are a
organic
lot.
also.
Yeah, I mean, organic materials, obviously, I mean, there is a lot of work being done, right? Organics afford you the luxury of cheap fabrication. You can
Okay.
fabricate using just organic dyes. You don't have to be in a very high class clean room and all. And we
Hmm.
already see that in the market in the form of OLEDs and all. And the other place where organic materials are being used is developing solar cells, right? We are trying to get flexible solar cells that you
Yes.
can create and put on your clothing or on any fabric or on your curtains, which you use on your windows and so on, right? So yeah, I mean, organic LEDs and solar cells are definitely being looked at, but at the same time, organic semiconductors, I think they lack the mobility to replace any inorganic semiconductors for transistor switching and all. Like microprocessors based on organic semiconductors. Um, I haven't looked at the recent one, but from my past knowledge, the mobility is really poor on those
No, no, not
semiconductors.
only mobility, but what about the stability? I'm only just concerned
Yeah,
about the stability point.
stability. Yeah, stability. I think with proper packaging, they have been able to get decent stability with the LEDs and solar cells. With the LEDs, I think they reached a good efficiency. That's why they are in the market. With the solar cells, efficiency is still a problem, so it's not in the market yet,
Exactly, sir.
right? But
And
stability, yeah, yeah.
what
You had
about
a
the
question?
this lifetime? Suppose that in case of 3 5 compound, it's a lifetime is so long, but in case of organic, will it
Mhm.
reduced or means reduce the efficiency within a short period of time?
Uh, for that, I cannot comment since I don't have data.
Mhm.
But looking at LEDs, I think they are doing well. No one
Well,
is
okay.
complaining that their TV is not working anymore or it is consuming
Mhm.
too much power, right? But yeah, I cannot comment on the other items for organics, like what's their lifetime looking at currently. But definitely inorganics, even in inorganic semiconductor, silicon and all, nitrides are the most robust. They are the
Right,
ones
right,
that
yes.
can take on radiation effect on it. So they are used a lot in the space applications. A lot of the chips that go into the space for communications and all are based on nitrides, because all the radiation that comes from the sun and all, they can tolerate it.
Okay. Sir, I have
Silicon and other semiconductors, yeah.
one question, that what are the scope of simulation work in this field? Because I have done some experimental work on the solar cell, but I have never done this LED and photo detector part. So what are the
So
scope?
simulation is really important, right? Because fabrication is expensive.
Yes.
So you don't want to find out problems by fabricating different structures. You want to do a good job at simulation and say like, okay, this is what my theory suggests. This should be the best structure that we have. Then we go and fabricate and check it out, right? That's the way the whole industry works. Like you don't blindly go and create a structure in the lab.
Yes.
You go with the simulation, right? And not just these fabrication of these LEDs and all, for all the microprocessors and everything, all the circuits you test it out in simulation, right? All the I forget the name of the softwares, Cadence and all.
Cadence.
Do that simulation, right? So before putting anything into the fab, we do a very diligent job of simulation. So simulation is as important as the latter part of fabrication.
No, sir, but I have a one doubt, that in the case of circuit part, it's okay. Cadence has a very good library, but in case of semiconductor, it's varying from lab to lab. So how we can?
So for that, I think there are different tools available. One is the APSYS tool, or Simu APSYS kind of tool that I worked with when I was in grad school. Right, it gives
Crosslight
you
APSYS.
Yeah, Crosslight. Yeah. So those tools you can try to create different geometries, 2D, 3D, or nanowires and all, and tailor the material properties that are being used over there. And thereafter check like if it's helping you, like is it validating your theory, or what would be the best structure that you should propose for fabrication, right? So simulation in these LEDs and solar cells goes through a different tool for sure. They don't go through that circuit tools, because the whole environment is different.
Sir, I have one last question. How industries like Intel is means working with means validating their because they are also not going directly with the fabrication, so they have to also do some simulation. So they are doing simulation on a particular tool, or we have to means calibrate regularly. What is the procedure?
So
the standard procedure.
Companies like Intel, I mean, simulation happens at different levels.
Okay, sir.
Right. One is the transistor level. Like they have to find out before putting a certain kind of doping or profile for the transistor. They do a simulation run. Like, okay, this we are trying to create this FinFET or whatever, or planar FET, and this gate width, this source width, this drain width, this doping, will it be good or not? Right. That happens at a transistor level. Then at the circuit level, they go with, okay, my transistor is capable of doing this. It can switch at this voltage. It can carry this much amount of current, and then it can do this type of frequency. So based on that, what should be the circuit, right? I mean, if I create a circuit of, say, flip-flops, my data should not be as slow. Like by the time it reaches the end, the next data is already in the flow, right? It should go really fast. So based on that, Intel and other companies go with the both kind of simulation environments, like transistor level, then circuit levels. There's also functional level simulations done, like just checking the logic of the design. Say you created a NAND gate, and based on that NAND gate, you created multiple NAND gates together, and then you wanted to achieve a certain logic. Does that work or not? In terms of logic, like just if you pass a 0, will I get the desired bit out or not? So that is another kind of simulation that has to be done, so that when you put it into a layout and that layout goes into the chip in terms of a physical transistor and all, it doesn't come out to be failing.
Thank you. So they are particularly stick with means tool like Synopsys or Silvaco for the process simulation of the device. Industry compatible.
I'm not knowledgeable of what tools they use for the transistor simulation and all, right? So I will not be able to comment on that. Yeah, but I do know that everything goes through a simulation.
Simulation part. Okay.
Yeah.
Processing. Thank you so much. Thank you so much.
Yeah. Yep. You're welcome.
Hello. Hello, Jay, can you hear me?
Yeah. Hey.
Okay. This is Aparna Dixit from Physics Department at our institute, Pranveer Singh Institute of Technology. I have one
Hello.
query. We have lot of students in EN department, EC departments. Lot of students are doing very hard work in their fields. So can we have some small projects for the student or some faculty member so that they will be engaged in some different kind of tools what you are using there, and like in terms of some small experiment that we can bear ourselves, or we can think in the field of theoretical research. So if it can be possible, yeah.
Sure, yeah, I'll think about it on that front, like what can be made possible. Yeah.
Because we are very hardworking and dynamic. If you give a chance to us to have some projects, so we can
Yeah,
be
definitely.
very thankful to you.
Yeah.
This was only my question only. So thank you so
Sure.
much.
Yeah, I'll think about it. Yeah, you're welcome.
Shant, uh, anyone is willing to ask question? Uh, yes, if they have any question, they can put their question on the mail ID also, on IEEE mail ID, so that these questions can be forwarded to Jay sir, and they will be replied soon.
Yeah, thank you, Dr. Jay Verma, for your valuable information given to the students. Really, it was a nice session. Thanks, Sushant.
Yeah,
And
thank you.
the feedback form have been placed in the chat box in both the platforms, WebEx as well as YouTube. It will be available for 3 days. Now, I want to call our head of the department, Mr. Anshuman Tyagi sir, to say a vote of thanks to Dr. Jay Verma.
A very good morning to our speaker, Dr. Jay Verma,
Yeah, thanks,
IEEE
Dr. Dev.
student chapter of PSIT Kanpur, faculty, student, and everyone attended the webinar on the semiconductor revolution. I, Anshuman Tyagi, HOD, Electrical and Electronics Engineering Department, PSIT Kanpur, extend a hearty vote of thanks to our speaker, Dr. Jay Verma, who spared time from his busiest schedule to grace the occasion. Today we had an opportunity to hear a technical session, and this will surely be going to be encourage us in our future events. My gratitude to speaker for delivering a webinar and sharing his knowledge today. I am immensely thankful to Dr. Aparna Dikshit, IEEE Student Society of KSIT, especially Sushant and Mr. Ramesh Sharma and entire Department of Electrical and Electronics Engineering for their effort towards conducting this webinar successfully. Thank you very much. Thanks, Jay, once again.
Yeah, thank you. Thanks for giving me the opportunity to come and talk. So, yeah, definitely let me know if anyone has any doubts. I know it was a lot of information in a very short period of time. So people might have got overwhelmed by it, but I tried my best. So thank you.
Thank you, sir.
Thank you, sir. Thank you, sir.
Thank you. Okay. Okay, thank you. Oh yeah, sure. Is there a way I
Dr.
should
Jay,
accept it? Or?
Dr. Jay, whenever you will visit India, it will be in your hands. It's my
Oh, okay.
responsibility.
Thank you. Yeah,
Thank you. Thank you.
yeah, I'll be there. Kanpur is my hometown, so I'll be there. Okay. Thank you.
Okay, thank you,
Have a
sir.
good
Thank
day,
you so
everyone.
much. I think the meeting is over. So thank you so much, sir, for all the
Yeah.
participants. They can be. Thank you.